Oh, it doesn't. Cool. Right. I'm Swapnil. I'm the head of innovation at Nethermind. And recently, I was in America, and I met these guys called Byte Piper or something. And they were talking about some compression stuff, and I told them, hey guys, you should look at blockchains. So now I work part-time for Byte Piper, and the idea is that we'll design the most profitable blockchain and make the most money ever. Byte Piper, as you already know, does compression really well. So the idea for Byte Piper is that we'll learn from the current state of the world and make a new blockchain which will be the best one ever. Cool. Before we get into it, what is blockchain? Blockchain is just a super base, so it's a database with edge functions, and there's some integrity. So you see a man there working really hard when there's loads of money on the other side. We probably won't be that kind of guy. What is blockchain for the degens? So the super base or the database with edge function for us looks like a block and some chains around it, and a smart contract which basically computes and updates and makes a new version of it for us. And integrity for us comes from the fact that our blockchains are decentralized, so no one person can mess around with it. So in the current world, how are we making these blockchains faster? So we are scaling the database, so we're storing the same amount of data with less resources, and this is where our DA's product comes in, Celestia, Avail, EigenDA. And we're scaling the execution by executing more programs faster with less resources, and this is where our ZK rollups and optimistic rollups come in. Cool. So looking into the DA side, there's a bunch of solutions. I'm going to go do a quick dive into EigenDA and how EigenDA works. So in EigenDA, there's a sequencer. Let's say it's a rollup. They collect the data. They send it to a disperser. And the disperser's job is to take this massive blob, make it into small chunks, and disperse it amongst the EigenDA nodes. In return, the EigenDA nodes send some signatures back saying like, hey, I have this piece of data, you can verify that I signed on this. And then the disperser aggregates it, so makes it one signature out of like many signatures, and puts that on Ethereum. So in effect, what's really happening is that we're taking a bunch of transactions, making a commitment off-chain, that some nodes off-chain have this data, and we're putting this commitment on-chain. If you really squint this diagram, it basically looks like compression. We're basically compressing the fact that some nodes outside the chain are storing some data that we're storing, and on-chain, we're just saying there's a commitment that there's nodes off-chain, we're just storing this. So now we know how to scale our DA layers. Now let's look at execution. There's a bunch of protocols doing that. Starknet, Arbitrum, Axiom, they're all basically following the same techniques. So I'm going to do a quick dive into how Starknet works, and this kind of applies to all ZK rollups and ZK processes. The idea is that there's the sequencer which collects many transactions from off-chain. It produces blocks. Then the blocks are sent to a prover, which generates a ZK proof of a block, and a ZK proof is basically attesting to the fact that the computation in the blocks was correct. Now, the one nice property of ZK proofs are that they're succinct. What I mean by that is that the proof for something is either constant side or is polylog. And again, this is basically starting to look like a compression algorithm. We're basically compressing the fact that the transactions in the block executed correctly and they produced a valid state transition. And once we have that, and we just put that compression fact on-chain so that people on-chain can verify that the computation we did off-chain was correct. Cool. I still have 7 minutes. I'm going really fast. Observation is basically Byte Piper all over again. We're basically compressing a bunch of off-chain data and putting it on-chain, and then people on-chain can verify this commitment that this was done correctly. Cool. So this is a really good thing for us. We know how to do compression, and we know how to do it really well. So we can probably design something better, but maybe we won't apply compression algorithms just yet, but we look further ahead, because these rollups and these DLAs are focused on compression, which we know how to do well. We look ahead what the problems are in the future. We'll solve those ones, and we'll make the most money. Cool. The fact that we're doing this compression, just some key points about it, is that we're doing compression off-chain and verifying the compression scheme on-chain. So for ZK rollups, we are doing the proving off-chain, and then we verify this proof on-chain. One key point to note about this is that compression algorithms need like critical amount of data to compress, where it makes it worth to amortize the cost of verification. And what I mean by that is that a ZK rollup, if it only posts one block of verification, it's really expensive for each transaction in that ZK rollup. So that's why ZK rollups are like batching like 200 blocks or something absurd, some absurdly high number of transactions, which also means that it takes a while to collect those number of transactions. And this also applies to our DA layers. They're not just posting like a file. They're collecting as many files as possible so they can amortize the cost of verification on-chain. And this point is going to be really key because it introduces a new set of problems. One thing that's really important, we talked about how we're scaling our blockchains by making the database faster and the execution, but we also need to make sure that the integrity part is still there. And how do we make sure that that is persistent is we verify these compressions on-chain. So you'll see loads of rollups saying that they're secured by Ethereum. What they mean to say is that they're actually paying Ethereum for its security. And that's like the crucial part that makes them a rollup, in my opinion. So the observation here is that off-chain solutions pay Ethereum a fee for the security. And since our compression algorithms are adding a delay, we also need to account for this delay in our payment to Ethereum. Because a delay in collecting fees from users and a delay in posting a message to Ethereum means that the L1 gas price might have changed by the time I'm posting to L1. It might have gone really high up or really low down. So in some sense, the sequencer is basically taking risk of L1 gas price, which doesn't sound really good for it. It could do some like naive techniques of charging fees always like 20% higher than the average, but it also means that the L2 users are paying more fees than they should have. So the sequencers realistically should hedge L1 gas price. Cool. So just as an example, let's say our Piper coin is a roll-up with amazing DA, and it wants to post a blob at this green line where the gas price is fairly low. But by the time it's collected enough transactions and it collected enough blobs, the gas price moves to the orange point. At that point, the L1 sequencer is paying a lot more transaction fees, and it's probably making a loss because it's paying because it collected transaction because the L2 fees that it quoted was based on when the L1 gas price was at the yellow point, at the green point. It also meant that it charged lower, and now it's paying higher to L1. So it's making a loss, which is not a sustainable profit. And if you remember, our job here is to make the most money, so we're probably not going to be doing that. Cool. So we now look at the design space of solutions that we can do. But before we go into that, we'll also look at some of the constraints that we have in the design space that we want to design. We probably can't do delivery of block space. And what I mean by that is, in the current Ethereum protocol, there is no provision for you to say, I want block 500 from now. Ethereum doesn't support this kind of transaction where I can say, I want the right to build the block 500 from right now. And to do that, we'll require massive consensus changes to Ethereum. It'll also require a lot more message complexity, something that we can't really do because the number of validators in Ethereum is so high. We're struggling with single stop finality, and if we add a new set of messages, it'll just make the network much slower. What we can do is deliver gas fee. So if you know the current design of Ethereum, there's a gas fee market called EIP 1559. And what it really says is that each transaction has to have a minimum base fee to enter a block. So what if we can design a market where we can deliver to the users the base fee for each block whenever they want it? And at that point, they have at least Ethereum anti-censorship guarantees to enter the block, and they also have the gas fees. So realistically, they should either make it in the current block or in like 2 or 3 blocks. That's the kind of guarantee Ethereum gives us today anyway. So we look at some projects that kind of try to do something similar in the past. There's a project called Gas Token, which was just tokenizing Ethereum gas. And how it did it was using refund system of Ethereum, where basically if Ethereum refunds you gas if you write 0 to a source slot or if you self-destruct a contract. And it's doing that because you're de-bloating Ethereum. You're removing stuff from Ethereum, and Ethereum is like saying, thank you for removing this stuff from me. This token was neutered after London fork because it was creating a lot of transactions which is just putting gas token, which doesn't seem that valuable for the chain and doesn't seem very valuable activity. Cool. So we'll probably look at some solutions in the traditional markets because all we're doing is seeing volatility and we need to find a solution to hedge it. The two financial instruments that work really well for this are options and futures. So an options contract is a contract that gives you the right to buy or sell an asset at a given in the future at a given price in the future. And the key thing to note here is an option. You can choose to buy or sell it. You don't have to buy or sell it. A future is similar, but the condition is compulsory. So it gives you the right to buy or sell an asset in the future, but you have to buy or sell it. You can't skip out on the deal. Now we look into some of the details of futures. In this case, we're also trying to price something in the future. So that's quite a hard auction to design, especially because Ethereum base fee is quite volatile, and we don't have a structured market for this just yet. And it's also kind of capital inefficient because we don't have a KYC system. So the person who's trying to buy the futures will have to lock up the capital at the time they want to, ahead of time. Whereas in traditional markets, because of KYC, they can just sign the contract, they can use the capital for whatever they want, and when the time comes of maturity, they can just put in the money. Options have the same problems. They're just a bit more capital efficient because the buyer of the option doesn't have to lock up their money just at the start of the contract. They can wait till the time of maturity, and then they can buy or sell the asset. So you might be expecting an amazing answer from me, but I don't have one yet. I'm just researching this topic. So if you have any thoughts about this, or if you're thinking about similar ideas, or if you work on this with me, please come talk to me. Yeah, but that's it. If you have any questions, I'd be glad to answer. Cool. No questions probably means that you all get it, and you all will follow me in my new startup. Thank you.
Thank you, Swapnil.